Yeah, I got a ping from Eric yesterday. I've been like super focused on like research and nothing else the last like week and a half, or maybe even like 2 weeks at this point.
Yeah, so like this is imperative that you sign this.
Okay. All right, I'll
like immediately.
Yeah, I'm also going to come to the meeting, so I guess I'm going to be like flying like tonight or something.
Oh, too bad you'll miss the concert.
Oh yeah, there's a concert.
Yeah, there's a concert tonight at Charles Finkelstein's castle. So Natasha, yeah, it's gonna be a lot of fun. Natasha and I are playing, and we have Ahmed Reza, who's a Kurdish drummer, who's playing with us, and Michael Henderson, who's a world-class oud player, who's playing with us. So.
And what time is that? What is that?
Doors open around 5, but I think we probably won't go on until 6 or 7.
Okay. I mean, I might make it. I'll take a look at flights and stuff.
Cool.
Well, you can get started if you guys want.
All right. I have some a sort of a live a visualization that I'll present. I'm just going to draw some stuff related to a protocol I've been working on. But I can do that at the end or whatever. So whoever wants to go first. Mine's a little involved, so I'll wait.
Sounds good. I'd be happy to share some of the things that I've been up to. So I've been working kind of hard on abstracting different pieces of like the construction and like seeing like what the minimum assumptions, models, definitions are that's required, for example, give the safety proof, and then like giving the kind of correct by construction approach like from there in like the most abstract way. And I've definitely been learning a lot, and I've gotten a lot of it written down. But I'm still working on it still, but I'm pretty optimistic about where it's going and about like how much it actually has helped me like reason about consensus and the correct by construction approach. So what I would also kind of like to go deep, but basically I have like I have like a super rigorous proof of the consensus safety like result for a super abstract consensus protocol. And
cool.
And I'm working towards doing the correct by construction thing, but if anything, I have a kind of really like solid definition of Byzantine fault tolerant like consensus consensus safety in a protocol. But so I guess I could go deeper, but let's just do like the whole breadth first thing. So anyone else have any updates?
Nate and I have been working on the CBC repo. I've been abstracting kind of the simulation runner into a way more reusable thing to be able to run experiments to gather more like analytic data about different distributions of validator sets and finality and different message propagation schemes, but more rather than just kind of seeing the visualizations, like running different experiments to get data on what's actually happening. So I'm going to be pushing on writing a few kind of sample experiments probably today. A lot of cleanup in general. The code base is definitely getting to a place where I'm going to be excited to release it. And Nate?
Sweet, that sounds great.
Yeah, so I've been working on like caching for an oracle. So you can kind of think of it like, if we check estimate safety on a message, it'd be good if we, or on some estimate, it'd be good if we didn't have to redo all the work if we check it again when we received one more message. So Vlad, you mentioned, I think it was like 2 weeks ago or something, that you had some code that did this before. And it seemed, so kind of the way you presented it was kind of like, after every message we receive, maybe a validator. So after a validator receives some message, like it does some constant amount of work to kind of update the viewables that it has, right? So there's two kind of approaches, I think. There's that, like, I guess I'm going to call it like a sequential approach, where like after every message we receive, we kind of update the viewables we have for the estimates that we're tracking. And then the other approach that we can kind of do is we can kind of say, well, let's like wait, and then we'll kind of do like a bulk update.
Yeah, totally. I had both implemented actually.
Oh, cool. Okay, cool. Yeah,
okay. Just the bulk update one where you just pass a set.
You pass a set of messages?
Yeah, basically there was basically you pass a set of messages, and then it figures out like what are the new observed ones.
Yeah, exactly. So I mean, so pretty much one way to do that is essentially just to look at the view and see which new messages we've had.
I had like basically I would basically just like include the dependencies until I reach the view, and then I would basically do this kind of dependency search that would be kind of stopped out at the view.
Yeah. Okay, so just looking at the view and kind of starting from each validator's, like saving the validator's last messages that you checked and starting from there is kind of more efficient than looking through the dependencies because we've kind of already sorted them, but when we put them into the view, if that makes sense.
What I'm saying is like, you look at the dependency until you get to their latest message.
Yeah. Okay, gotcha.
Further, right?
Yeah.
You only look so basically you look in a way where that like you kind of only keep looking as far like until you don't have any possibility of seeing any new messages.
Yeah, and the other thing we kind of do is when we're looking through the justification, like when we start from the most recent message and kind of work our way back to the view latest message, as soon as we find a viewable, we can kind of stop looking.
For that estimate value, right?
Yes, for that specific estimate value. And as soon as we find like, what I'm calling a free block, but what is really just a conflicting estimate, as soon as we find the first one, then we can kind of stop looking. And that's kind of
for new latest message. Yeah. For a new latest message with conflicting estimate.
Yep.
But basically like with the viewable thing, I mean, we want to set it up for any Oracle we might run later, not just for the estimates we have now.
Yeah. So, okay, there's two things here. So, or when you say that, do you mean that like we should store all viewables for that estimate?
No, one viewable for each estimate.
Right. So okay, cool. So in that case, then we should always store the most recent one, right? Because in that case, we're kind of just assuming it's going to be side effects free for every Oracle we come up with.
How are we assuming that?
If you're only storing the most recent viewable, then kind of
I want to store one viewable for every validator for every estimate. You can imagine, like for every estimate we're in conflict.
Okay. Yeah, I get you. I think that kind of like from like a complexity standpoint, it only really makes sense to store the most recent one.
In terms of the viewables, yeah, absolutely. I think storing the most recent one is the best, but you store one most recent one for each of the estimates.
Yes. Yeah, totally. But the only point that I'm making is that kind of makes the assumption then that all the oracles we'll ever define kind of operate in the side effect free thing, right? Because then we, if we, for example, we were to make a non-side effect free adversary, we wouldn't be able to do a search on that over all viewables. It's just the most recent ones.
Okay, I hear you.
Cool. Yeah. So anyways, the bulk updating thing I think is more efficient. And
cool.
Yeah. So just been working on that.
Yeah, that's super cool. John, any updates?
Yeah. So I emailed you the article that I recently posted about Casper 101. So I think that's kind of meant to be like a jumping off point for people that are new to Casper, so that I think it's really timely for the CVC paper coming out and all the code coming out, because it goes over all of your history of Casper. I think you did a really good job kind of noting what are the Casper design principles. And this is kind of one place that aggregates all of that. So if you haven't taken a look at of the final version, take a look. And after this, I think I'll be focusing on the incentives and FFG paper, but kind of open-ended on what I'll be working on next. But I feel much more caught up on the CBC stuff, and I'm going to take a look at the paper and see how it can be helpful.
Cool. Yeah, so I guess if no one minds, I will do like a quick dive into the safety proof, and then I'll give Greg a time to do some screen share.
Yeah, good. Sure.
Let's see. Here we go. Sorry, I'm trying to figure out how to do screen share right now. Oh, here we go. This is a big button for it. Great. Check it out. So here's like the paper. I'm not gonna give you guys really like that much time to read it right now, but basically the point of the paper is like to give this correct by construction approach, and then to give a couple of protocols to satisfy the definitions required to benefit from the proof in the correct by construction approach. So basically, and the idea is I'm going to try to have a kind of general abstract definition, which we kind of refine until it comes to the point where a reasonable consensus protocol definition, or where it's something that anything that satisfies the definition is a consensus protocol that benefits from like the proofs given in the correct by construction process. So basically, the way that this paper is structured is like, at first, I'm just going to present the minimum definitions required to give the consensus safety proof. And then we kind of build on, and then we like add things like non-triviality and, the like communication, stuff like that, after giving the consensus safety proof. And eventually we get to a point, hopefully, where it's quite easy to construct a consensus protocol. But in any case, if we do manage to construct a protocol that satisfies it, we benefit from all the proofs, even if it requires like a bigger leap. So basically, we have definition of the first part of the definition of estimate safety consensus protocol. It's gonna basically have like four things. You have like possible values of the consensus, logic, whose propositions are satisfied or not by those values, a set of protocol states, which is like a category, and an estimator, which maps the objects in this category to propositions in this logic. So basically, there's like some things that we might come to consensus on, and then from every protocol state that we're in, we have a map that maps the state to propositions about those values. And this is kind of our setup. And the category of protocol executions have basically objects called protocol states, and then maps called executions. And basically, like, the executions compose. So if like, a protocol executes from like one state to another, and then from that state to a third, then it executes from the first to the third also. And we have an identity morphism so that it like maps to itself. Sorry, I basically have like the category properties for the state object, for the protocol state with execution object. Category. And then basically the logic has negation and Boolean operators. And basically we have the estimator having the property that if the like propositions returned by the estimator imply some proposition P, then it won't be the case that the same estimator implies not P. And this is kind of everything we need to give our safety proof. Basically, we have this local notion of safety called estimate safety, kind of where basically the estimator is going to imply this P for any future state sigma prime of this state sigma that we're saying is safe on P. So like P is safe on the state sigma. So if all future states imply P, then P is safe there. So like if you have a state and all future states have this estimator imply some value, then that's somehow safe. And then the idea is that like, okay, if it's safe, then it's like we're gonna be cool to decide on it, because like safe things by virtue of like always being in the future have this like monotonicity that like decisions do. And then basically we want to show this a result that says that like these decisions actually have consensus safety, even though they're kind of only defined in terms of this local property of the node of the state sigma that the node is in. And basically we're gonna have like this little squiggle, which indicates that two states have a common future. So there exists some third state which they can both execute to. And then the consensus safety theorem basically says that like, okay, if you have this, then you don't have them being safe on contradicting values. So like P and not P. And basically it says like, okay, if there's a common future, then there's consensus safety. And basically there's like a few lemmas, and then there's like a proof to the theorem. So the first lemma basically says that like if sigma 1 is safe on P, then like sigma 3 up here will also be safe on P. So basically it says, okay, look, if we have sigma executing to sigma prime and sigma is safe on P, then sigma prime also will have safety with P. And I have like a proof here of this. Basically, okay, we're going to assume that sigma goes to sigma prime. We have this like morphism composition thing from the definition of these morphisms, really. And we can kind of combine these two facts to show that, okay, well, if anything is a future of sigma prime, then it's also a future of sigma. And we have like safety on P for sigma, which means that for any sigma like star, which is an execution of sigma, we have that the estimator implies P. And these two things kind of together mean that sigma double prime, which is a feature of sigma prime, also will satisfy P. Also will have an estimator that implies P. Because sigma double prime is a feature of sigma. If sigma double prime is a feature of sigma prime. So we kind of can conclude this from this and this. They even really line up. So you can see that this implies that with the substitution of sigma double prime for sigma star. And then this is actually the definition of safety on sigma prime, because it says that any feature of sigma prime is going to imply P. And so that's kind of like the proof of lemma 1. Lemma 2 says that like if we're safe on P, then we're not safe on not P for the same state. Surprisingly, it took me many lines to prove this guy, even though it's like super simple. because basically I have to go down and so firstly, like, okay, we have an identity morphism, so we can use the safety on P just to include that to conclude that the estimator implies P for sigma. So the safety at sigma for P means that the estimator at sigma implies P. From the definition of the estimator, we know that that means that the sigma doesn't imply not P, which means that the estimator doesn't have imply not P because we have this fact that it does imply P. And we can kind of do this exactly symmetrically to show that the estimator that if we were safe on not P for sigma, then we would have the estimator meaning implying not P, and then like using the contrapositive, we kind of can get that the fact that the estimator doesn't return not P means that we're not safe on not P. And that's kind of like the theorem there. It's mega straightforward, but I wanted to do it kind of line by line. And then there's like the backwards consistency theorem, which is kind of an interesting one. Take a look at this photo. So this one says that if this one is safe on P, then sigma 2 is not safe on not P. So kind of is like another not safe not P situation. But this time, rather than being for like the same state, it's for like any state that executes, any previous state. So, and the proof here is quite shorter. Basically, okay, well, if sigma prime goes to sigma, then we know that if it was safe on not P at sigma prime, then it would also be safe on not P at sigma, just by lemma 1. Which by lemma 2, which the one we just showed, that means that like, okay, we don't have safety on P at sigma. Which means basically that if we didn't have safety initially, if we had safety on not P on sigma prime, then we won't have safety on P at sigma, and the contrapositive of that is just kind of our result. But like intuitively, the way you show this intuitively is by like proof by contradiction. You basically just assume that sigma prime is safe on not P, and use that to like contradict the fact that you're safe on P at sigma, and then therefore conclude that you're not safe on not P at sigma prime after all. It's really simple proof, but rather than giving it by contradiction, I just use the contrapositive because it's easier to like audit. And then finally, the proof of this consensus safety theorem just uses lemma 1 and lemma 3. Where basically, if we're safe here, sigma 1, then we're going to be safe at sigma 3, which means we're not going to be not safe at sigma 2. Which means that basically like safe on P at sigma 1 implies that we're not safe on not P at sigma 2. And basically by like the three last lines of the proof here, we're safe on P at sigma 1 implies not safe not P at sigma 2, and implication basically just means like not safe on P at sigma 1 or not safe and not P at sigma 2, which by De Morgan's is just not safe on P at sigma 1 and safe on not P at sigma 2, which is the kind of consensus safety result for the decisions that happen on safe estimates, which is kind of our context. And then we also have this property that safe on P implies not safe and not P. Is kind of in some way the intuition is different and maybe a little more interesting than the consensus safety thing, because the consensus safety thing says, okay, if they're both safe, then they can't be safe on P and not P. This these are equivalent, but this says more like, okay, if I'm safe on P, then no one else who I share a common feature with is safe on non-P. It feels like, it's less information, even though they're kind of equivalent. And then, non-triviality means that there's going to be a couple of states which don't share futures, which means that it's not that easy necessarily, or there are going to be failure modes where this shared future thing on the left of the consensus safety proof isn't going to hold. And you can show that using non-triviality and the contrapositive of the safety proof, which is kind of interesting, as consensus failure implies that they don't have a shared future. I have this little drawing, kind of showing that like nodes with shared futures are kind of on the same like path through this like forking thing. Nodes without shared futures have this property that they kind of have like no way to ever join up again. And so they may have made decisions that about to like on irreversible stuff. But if they have made decisions on that are irreconcilable, then definitely they won't share a future, and like this might be like a reasonable way to represent it. I mean, I feel like it becomes a lot more reasonable if I assume that, like, say there's no stuck areas. Like there could conceivably be an area here you can get stuck and then never make this choice. But if you don't have that kind of thing, then I think this is kind of representative of what consensus protocols look like. You have these like forking paths through protocol state space, and then you have nodes trying to maintain like to like always choose the same forks through the path, which is basically, I mean, maintaining a shared future is sufficient for that. Is basically what the consensus safety proof says. Basically, it says that like maintaining a shared future is sufficient for consensus safety. And so like that's kind of a pretty, in some way a pretty basic result. But it is like a safety proof that like we use in the correct reconstruction kind of protocols, and is actually quite useful, because basically like it gives us a way to locally make decisions that have consensus safety as long as we make sure that we have a common future. And the plan is basically going to be to make sure that like as long as there's less than some number of Byzantine faults, then we will have a common future. But to define Byzantine faults, we need to kind of add to our definition somewhat. So basically what I do is I kind of have, okay, well, that was kind of somehow I gave protocol executions as like a kind of trace or like a string, like, path through the category. And now we're going to consider kind of like n of them, like n executions through the protocol. And so then we get to have like kind of n nodes executing through the protocol concurrently, and we can make kind of a category out of that, and allow, and we can actually restrict the state transitions, or like the morphisms in this higher category, to only allow ones in the, or like I'm not sure if it's higher category in this other category, in order to only allow morphisms in this category that maintain common futures between all the nodes, which means that they'll have consensus safety. So we can define this like category sigma 1, which is the category which basically describes the consensus safe executions of the consensus protocol in sigma, which we talked about kind of earlier. And then we can kind of go further and have sigma 2, which is a bunch of executions of sigma 1, which again are each a consensus safe execution of some consensus protocol. And then we can basically have like what essentially in sigma 2 is like, a model of n nodes watching n nodes execute a consensus protocol. And it turns out that like in this category, we can define equivocation when there doesn't exist a kind of path through the different states that were attributed to any particular node. So like the nodes have to have kind of like a unique path through all the protocol states that they, like they kind of have in the object, in some objects in the category. So we can kind of like restrict the number of equivocations. And so basically, like with that, we can kind of have we kind of have this the sigma 2 be n essentially n nodes watching n nodes execute a consensus protocol without more than some number of equivocations. And we can also kind of insist, as before, that there are common features between the elements of sigma 1, and then like sigma 2 becomes like this description of like a consensus a Byzantine fault tolerant consensus protocol that has consensus safety. In the context of that number of faults. And so then this becomes like kind of the definition that like the correct reconstruction process should like, aim to satisfy, or like that the protocols that are derived to satisfy the safety proof should satisfy this thing. Anyways, it gets kind of complicated pretty quick, but the safety proof itself is actually very, very simple. And I'm hoping that like everything else will be simple at the end of the day also. But basically, it's still a work in progress. But basically, the main thing that's kind of happened is I've moved a lot of the kind of core of the safety proof up to a much more abstract definition than I was using before. The kind of old stuff actually does satisfy all of this stuff, and is like kind of a guide for me in some way, where I basically like wanted. I mean, the strategy for maintaining shared futures, for example, is to always be able to go to some state which is like the union, which is like some like function of the union of our views, if there's less than some number of Byzantine faults there. And that will make sure that as long as there are less than some number of Byzantine faults, then we will have a shared future, which means that we will have consensus safety in that context of faults. Or kind of using the contrapositive that like if we have consensus failure, then we don't have shared futures, which means that we will have more than that number of faults. And that's kind of like the setup. I'm pretty happy with it in a lot of ways, but I also think that there's still a lot of work to do probably. I don't know. Anyone have any like questions, thoughts?
I have a few questions.
Sure, go ahead.
So first of all, kind of the most fundamental thing: are you beginning with an axiomatic framework for a bunch of validators interacting with each other and then proving that you have a category, or are you beginning with a category?
I'm beginning with a category and then generating a bunch of validators.
Okay, so you identify validators as entities within the category.
So basically, no, it's kind of more like so. I mean, I'm gonna have like so basically, I have a category for executions of the protocol for any validator.
Okay, so then you have to pony up a proof that it is in fact a category.
So I mean, I assume that I have a category. If I give an implementation of it, I would have to pony up the proof.
So you begin with a category and then you have to find the validators.
Yeah, which I do with like tuples of objects in that category.
Okay. So that was the because I'd written at you about this before, right? And before it sounded like you were beginning with validators and you were going to find a category of protocol states and evolutions out of protocol states. In which case you have a proof obligation that this is that composition and that you have a notion of composition that's associative and has identities.
I think that you will have that in practice, like when you actually run the process, because you'll have to come up with something that that satisfies the definitions that like are given, right? But for actually giving the correct reconstruction process, I don't need to actually say what the category is.
As long as but then you have to find the validators within the category. You have to say, okay, I've got some ambient category, and these things inside the category represent validators.
More like I have a tuple of objects in the category, and that represents like a bunch of validators, each executing the protocol.
Right. Yeah, and whether they're tuples or they're or sheaves or whatever your your thing that you're building over top of your category, you have to find a collection of widgets that are related to this ambient category that represent validators.
Yeah.
Okay, so that's helpful. And then the morphisms represent future states. Is this correct?
Yeah, protocol executions. Yeah, like future states. Yeah, future states of protocol. Yeah.
Okay. All right. Cool. Just making sure I've got the. And then your representation of propositions relative to the category. So there are lots of different ways to do this. Ladle has one approach. There's a notion of sub-object classifier, and the approach of Levere. So are you introducing either of those, or is this a new thing?
I'm kind of assuming, basically, like I'm kind of, I don't know that much about what the logic is going to look like, but I do know kind of that I basically need like negation, implication. I need to be able to do like to take like to use like and or like I just need like a few like just a small number of basic things.
Okay, cool. I mean, it sounds like, so do you have excluded middle?
Yeah, I do.
Okay,
but I do also, but I kind of cop out in a way where my estimator doesn't actually necessarily need to return something which you could use to like conclude whether something is true or false. Like there might be like a P such that the estimator doesn't imply P or not P. But if it does imply P, then it does also imply not. Then that implies that the estimator doesn't imply not P.
Okay, so well, I mean, excluded middle is
not P, really.
Yeah, exactly. So excluded middle means that the implication runs both ways. So usually you can get one direction if you're intuitionistic, but you can't get the other. And so it sounds like, based on the direction that you have, that you really do have excluded middle. Okay, cool. Just checking to see what the core of this thing is.
And I would love to talk more. I would love to talk more about that.
Yeah, I mean, the reason I'm asking is because based upon like here, the difference between Ladle and other logics is that Ladle, the kind of connectives you're talking about are what I call connectives that come from a collection. So the collection sounds very much like a power object collection, right? So set of all subsets of something. And that will give you the ands and the ors and the implications and negations that you need under certain reasonable constraints on what we mean by power object. So like set of all subsets of something, or set of all subgraphs of some graph, or that's what I mean by a power object. And it sounds like that the the connectives you're talking about derive in that way, in a very natural way. Ladle is more powerful because it also, in addition to the connectives that come from some collection object, whether it's a power object or something weaker or something more elaborate, like the set of all subsets of sequences of something. That's another kind of collection, but it gives you a linear logic as opposed to just a kind of classical logic. But Ladle also gives you the logical connectives that correspond to term connectives. So in this case, you would have for your consensus states, you could have a language that describes the states themselves or the shape of the state. So, for example, if you have tupling as a state constructor, then you would have a connective that was related to tupling, and which is not something you get out of the power object or collection object piece of the puzzle.
Cool. Yeah, that seems neat. I mean, I wish I knew more about like that. And I think, the logic that we use to ask questions about the state of the consensus, at the end of the day, has to be something that we can, calculate safety about, and something that like is related to what users want to know about.
Yeah, and the reason this is important, is most important, is because as we discussed a few weeks ago, what you're describing as safety has to do with the modal operator necessity. So they're intimately related. And I'm not sure that everyone watching knows. So necessity and possibility, going back all the way to Kripke's interpretation of those operators, are related to states you can reach from here. And your safety property is saying something about all the states you can reach from here. So necessarily some property has to hold. And there are different flavors of this, right? Because a lot of necessity that's formulated as all the states you can reach from here is not actually computationally feasible. It becomes undecidable. But all the states you can reach from here in the next step can be computationally feasible, and then you can give weaker versions that extend that, next step after in steps that can be made computationally feasible. And so having a nice relationship between the logical operators that are used to describe future states and having a fine-grained decomposition gives you a fine-grained handle on when your search for formulae is computationally feasible and when it's going to run up against decidability issues.
Yeah, I mean, we have like all sorts of kind of shenanigans that we do to like get like just decidable kind of, or like to get an assessment about whether something is actually safe.
Yeah, I understood.
The theorem applies to things that are safe. It doesn't actually say anything about how we actually find that.
Yeah, understood. Yeah, so it may be that you have a notion of safety, but computing it doesn't ever halt. So that would be,
doesn't ever halt.
Yeah, so you just don't get an answer back. So you go and ask, you say, is this safe? And it says, oh, I'm thinking. And after a little while you say, well, and the answer is still thinking, and the universe is much older, and you say, so is it safe? Still thinking. So those are things that arise out of saying things like all future states.
I mean, kind of. If you can't like solve some math problem that where you conclude that there is something about all future states. I mean, it's not like necessarily going to end up like that. I mean, we can and like do in like all the protocols that we really like generate have.
I have to. Yeah, that's all I'm saying is that we want to look at the framework really, really carefully because under the all future states rubric lies a lot of dragons, and so just having a nice fine grain, and that's the reason I'm mentioning ladle. It's just having a really nice fine grain set of controls over how we reason about future states and how we relate those to propositions. Ends up being useful because you can avoid the dragons. That's all.
That sounds interesting.
Yeah. Cool. So
I thought Danny said that he had some questions also.
Yeah, exactly.
What? No, I didn't say anything.
Oh, someone said something. I don't know who it was.
We can talk about this after, but I'm going to be digging into the paper after this call, and I'm just want to get a read on which parts are ready for, like, proofing and stuff, and which parts.
Yeah, I would say like a part like 0 and part 1.
Okay, cool. Well, we can connect after this, and
Okay.
I'll start running through that.
Okay. Well, I guess Greg, go ahead and give your update if you know.
Yeah, sure. Largely, I got distracted this week thinking about a protocol for authentication and identity that we need in a bunch of different contexts. So yeah, I was off the mainline Casper stuff, but I can. It's a kind of cool protocol, and it helps people understand how to think about programming in Rolang. So I'll give a quick show of what I'm talking about here. So one thing is that agency in Rolang, whether you're talking about people like Abed and Troy, or talking about contracts, which may in some sense be proxies for Abed and Troy, they sort of look like these generalized braids. So if we think of these things across the top as channels or ports, then this behavior here is parametric in these channels, and then all behavior is essentially sending messages from one channel to another. So hopefully that's super clear. Can everyone see what I'm pointing at?
Yep.
So then for Abed and Troy to communicate at all, they have to have some group of channels that are in common. So I've selected those. I'm just going to give a visual aid to talk about which ones are in common here. So let's say that these are the ones in common, and so I'll do that, and maybe make this be a dashed line. I don't know if I updated my oops, wrong one. I updated my OmniGraffle foolishly, thinking that all right, well, looks like, oh wait, maybe this is it. Yeah, here we go. Do a dashed line like that. So those are the ones that are in common. Whoops. Here we go. From here to here, like that. Okay, so those are the ones in common, and they're able to communicate across each other because they share these in common. And in order to have something in common at all, that means there's some scope where a channel came into being, like this outer scope here, and that channel was provided as a parameter to Abed and Troy. So that's what this little diagram here is. And now what we're kind of interested in is that these scopes where channels are created are a little bit leaky. So Abed and Troy can't really tell if, let's say Abed creates an email address, right? And that's what's supplied here. So that maybe this channel is really you could think of that as the SMTP inbox or something. There's lots of different ways you can think about it. But so Abed creates an email address, and because Abed doesn't really trust the email system like with his life, he assumes that email address might be leaked at some point. Likewise, if Troy gets a new phone, and this one represents a phone number, then they can't really trust that phone number isn't being eavesdropped on. And so someone, if they were just relying on one channel, then they're not convinced necessarily. Abed is not convinced that he's talking to Troy, and Troy is not convinced that he's talking to Abed. So that's kind of the framework in which I've been thinking about this protocol. But just in the same way that we sort of informally do this, or it's more formally done with a two-factor authentication. If Abed sends on email and says, please respond on text. So Abed sends a message on email and says, and in the message says, please respond on text. And then Troy sends back on text. Then that sort of gives Abed at least some confidence that he's talking to Troy as opposed to someone else.
And this is like without digital signatures, like
digital signatures are a part of the puzzle, but this is again, we're assuming that you can't really trust that someone may have at one point eavesdropped and compromised the signing process. That's the assumption. And so the question is, can we do a little bit better than that? And the thought that runs throughout this is that it is twofold. So we're using both logical description, and we're using something that is stolen from the biology world. So in biology, there's a thing called kinetic proofreading, and essentially, and you can look it up here. Let me grab I heartily encourage people to read about kinetic proofreading, because it's a way to turn energy into signal fidelity. It was discovered by John Hopfield, who is the inventor of neural nets. So essentially, it's a way to turn energy into signal fidelity. So you know that you're increasing the likelihood or the fidelity of the signal, the quality of the signal, if you put in energy. And it has to do with you've got two reagents. They can bond for a short period, and then there are two ways that can go. So they bond for a brief period, and either the bond can dissolve, or it can be promoted to a new state, in which case the bonding is a little tighter. And then if you sort of have this multi-step ratchet, and if you just go through the stoichiometry of this, you can show that and the important thing is that you have differential rates between the fall off versus the promotion. And so what we're going to do is we're going to do exactly the same kind of thing here in this protocol. So in this protocol, what happens is that Abed doesn't send, there isn't a pre-specified send me back on text. Instead, just as like maybe you see when you change your password, there are some options for where to send the second factor, right? That there's a choice. Here, what we do is we provide a namespace, which is going to select a subgroup or a sub collection of the set of channels that Abed and Troy have in common. And then it suddenly becomes much less likely for an eavesdropper to be able to pick out all of the channels that satisfy the namespace. So again, a namespace is like a logical description of channels, and only some of the channels in the common core, or that Abed and share together, will satisfy this logical description. And then so Troy does a check and says, it's It's this group here in the middle, not these two endpoints, let's say, and then selects one from there, and then responds on that. Now, Abed has a great deal more confidence, but the nice thing is that Abed and Troy can iterate this process. So it could be that Troy doesn't necessarily trust that Abed is in fact the one that that did this, and so Troy can iterate this process and send a namespace, which again selects some subgroup of channels that they share in common. And for each step in this iterative process, they can keep going back and forth. And with each step, you can get a kind of qualitative improvement, because first of all, there's the energy associated with the computational check that which channels satisfy the namespace descriptor. And then there's the energy that goes into selecting. And this is, you can think of this as a little bit of the introduction of a little bit of entropy, the energy of selecting one of the channels. So those two combine and give you the energy input that is the part of the multi-step ratchet in kinetic proofreading. And so essentially what you get over time, you get this method. And in fact, it's not bound in a certain way because they can always create new channels. So it's not bound to be confined to this initial common set. The common set can grow and can shrink over time as a part of the protocol, but they can put in as much energy as they want, and we can calculate how much the certification or reliability that it is indeed Abed talking to Troy and Troy talking to Abed. So that's the basic setup for the protocol. Not bad. I did it in about 5 minutes. So any questions?
I mean, I wish I could understand this in terms of like an adversary or some kind of crypto thing.
Well, the adversary is think about it this way. The adversary can sit here in terms of the adversary largely is about the scope that's associated with the creation of channels and the potential leakage of channels. We can assume no eavesdrop unless you have the channel in hand. So you have security through obscurity, right? In the sense that if you don't know which of these channels to listen on, then you won't necessarily listen on it. So that's the security model. And so the adversary can learn about a channel, and then the question is, which channel can it learn about? And it has to be able to, as long as they're continually channel hopping, then it becomes harder and harder and harder for the adversary to figure out which channel to listen on. And each hop step sort of describes a set of possible frequencies. Think about it like, they're twisting radio frequencies, right? So Abed says, listen on these frequencies, where these frequencies is not a specific list of frequencies, but rather a rule for selecting frequencies. And then Troy can go and figure out which of the frequencies Troy has that actually fits the rule, and then select one, and then from that frequency send to Abed. But what he sends is again another rule for selecting frequencies. So step by step, they kind of they're sort of twisting the dials and communicating rules for which frequencies to listen to.
So these are entities and messages passed on or say in a blockchain protocol, but can they be communicating on frequencies that are extra protocol? Like, can Abed say to hit me up via text or some more automated method, and then send a message about getting that?
Yeah. So the it's not required that it go over blockchain, but it can work with blockchain as well. So the protocol is quite general.
Right.
Yeah, that's the idea, is that you have these leaky. It's designed for scopes where the channel creation is potentially leaky. So for example, when Abed requested an email or a phone number or any other means of communication is generated, Abed is then required to trust the generator of that endpoint, and that's a trust step that Abed may not want to make.
Right.
So even in the context of having that kind of lack of trust in the endpoint generators, the protocol can still create a more or less secure. It's a qualitatively secure protocol between Abed and Troy. In other words, they get to have as much certainty about the parties on the other end as they are willing to put energy into the protocol.
Right. Cool.
Yeah, it's kind of fun. Awesome. We're way over time. And any other updates?
I guess not.
Yep.
Cool. So next week is the day before DevCon. Are we going to do this?
Well, I mean, let's plan to and see what happens.
Sounds good.
Yep.
Cool.
All right, guys. Have a good one.
Bye, everyone.
Yeah. Thanks, everyone.
Bye.